participants. I hope you can able to hear me and also you can able to see my presentation. So in the FDP, there are multiple people joined from interdisciplinary engineering branches. So we thought of going with the introduction to the industrial robots. So the robots typically, it comes out of the efforts of mechanical, electrical, electronics, and computer science engineers. So everybody has their own piece of work in the robot to function well in its real-time practice. So I felt like starting to give an introduction to the industrial robot, then taking you through the advancements. So this session is planned to give the introduction to the robotics. So the contents are planned like the human civilization and the robot, the terminology and classification of robot, the robot characteristics, elements of robot, the grippers and sensors that used for the robot, and the selection of robot, and accidents and safety of the robots, and applications of industrial robot, and installation checklist. Finally, with the future industrial robots. So the human civilization and robot, if you see the size of the brain, which started increasing rapidly during the human evaluation. So the scientists say that the increase in the brain size allowed to the development of complex tools and innovations for the mankind. And you can see here the picture how the brain size is increased from 600 cubic centimeters to 1350 cubic centimeters. If you trace back the Stone Age, initially the human mankind was using the stones as the tools for the food. So from 3 million BC to the 1.9 million BC, the humans lived as hunter-gatherers. They were dependent on hunting the large prey size and then the medium prey size with the tools. And mostly the stone-based tools were only used to hunt the animals. And you can see the growth of the brain size is 650 cc to 1500 cubic centimeters. So this evolvement is a very slow phase if you consider from 3 million to 0.3 million of BC. So till the 12,000 BC, the humans were mostly dependent on, mostly lived on human hunter-gatherers and then started the cultivation in the year of 12,000 BC. The end of the Stone Age, 5000 BC, where the humans started thinking for the tools which supports the cultivation. So certainly evolved with 6 simple missions in the early stages of the Bronze Age or the late stages of the Stone Age. These 6 simple missions are still a part of our life. The first one is the lever, the second is wheel and axle, third is the pulley, fourth is the inclined plane, and fifth is the wedge, and sixth is the screw. Most of these simple missions were used for the agricultural purpose. The lever is a simple mission made up of a rigid beam and fulcrum, so which you can use it to lift the heavier loads with the smaller effects. And you can see these kind of mechanisms, the principle involved in most of our day-to-day elements. And the next thing is the wheel and axle. So here there are 2 cylinders, one with the larger radius, another with the smaller radius. Typically the smaller radius cylinder we call it as a shaft, and the bigger radius cylinder we call it as a wheel. So you can transfer the load from the bigger wheel to smaller wheel or the smaller wheel to the bigger wheel. So this kind of mechanism was used initially for the agricultural purpose to lift the water for the cultivation. The third thing is the pulley. So pulley is a wheel on the axle or a shaft to support the movement and change of direction of a taut cable or a belt. So typically the pulley transfers the power from it to the belt, which is further connected to another pulley. So you can see here, this is actually called as block and tackle mechanism, which you can see this kind of thing in the ports while picking the heavier loads and placing it. The heavier containers in the ship harbors, you can see to the cranes. This block and tackle mechanism is basically based on the pulley system, where with a small effort, you can lift the heavier loads. And the fourth one is the incline plane, which is typically used to lift the heavier objects to the heights or to move it to down in vice versa. The fourth one is the wedge, which is mostly used to cut the plants on the trees. You can see that in the axe. So it can change the direction of the force in other perpendicular directions. So the final one is the screw mechanism. So you might have heard of Archimedes screw principle. So which can transfer the motion from rotational to the linear, which initially used for lifting the water for the agricultural purpose. These six are the simple missions generally. Some of you might have seen or read this during your engineering mechanics starting. So these six simple missions were evolved during the late stage of the Stone Age or the earlier stages of the Bronze Age. But still, we are using these six simple machines with their mechanisms. And now we have come to an Industrial Revolution 4, where there is a huge and rapid change in this machinery and equipment for the better manufacturing and higher productivity of complex goods and products. So if you look at a mission, so generally we create or fabricate a mission for a specific purpose, which can do only a single task, and you cannot train a mission for a specific task, and the degrees of freedom of a mission is completely constrained and it cannot think on its own. So the humans have come up with a multi-tasking missions with which can capable of doing multiple tasks with higher degrees of freedom. So that's what we are calling as robots in nowadays. And robot, which is evolved from a chess word robota. The robota means a slave like lever in chess. So the basic definition of robot is from the Robotic Institute of America. Robot is a reprogrammable and multifunctional manipulator which is designed to move the material or parts or tools or specialized devices through variable programmed motions for the performance of a variety of tasks. So we generally use this robot to do the repetitive tasks and to handle the heavier objects and to attain maximum accuracy in manufacturing and to work in the hazardous environments. So these four are typically, we can say, the limitations of the humans, what we cannot do. If we do the repetitive tasks, we will tend to the fatigue, or our musculoskeletal system doesn't allow us to do it repeatedly. And there the ergonomics play a significant role, which can be avoided by replacing with a robot. And of course, with the heavier objects. And the accuracy of the robot is obviously high with an appropriate control systems associated with the robot. Now let us look into some terminology that we use with the robots. Here you can see the animation where we can find out some links and joints with a defined motion. The link is a rigid member connecting to the joints, where the joints are the movable components of the robot that can cause the relative motion between the links. So we are going to supply some power at the joint. So the joint will give the moment to the link associated to it. So based on the number of joints, we define the degree of freedom of a robot. which is nothing but the number of independent movements the robot can exhibit in the three-dimensional space. So the more number of degrees of freedom to a robot makes it so flexible to do a specific task. And here you can see this is a robot soccer challenge for 2022. So the scientists are trying to come up or replicate a humanoid robot which can have the highest degrees of freedom to play a football with the winner of the soccer 2022. Still, this is under progress, which is a very complicated task involved with a lot of dynamics and control systems and artificial intelligence. Now, let us look at the types of joints that we use in the robots. So the first one is the linear joint. The types of joints here we are naming based on the axis of the links. If you see here, the input link and the output link, which are aligned in the same axis, and the moment of the input link, the output link is along the axis. So such type of joint, we call it as a linear joint. You can see the blue color one, which is sliding over the gray one. So the axis of both the links are collinear and coaxial, and the moment is also in the same direction of the axis. If the output link is perpendicular to the input link, the motion is perpendicular, then we will call it as orthogonal joint. So you can see it. So here the moment is along the X, Y, and Z directions that you can see for all these sliding links. And there are three other joints named as rotational, twisting, and then revolving. So we are going to differentiate all these three joints by means of the axis of the input and output link and the rotational axis. If you see the rotational axis is perpendicular to the input and output link. Let us say that the input and output links are in the XY plane. The output link is rotated with reference to the Z. You can see that in this animation. Now, if the same case, the input and the output links are in the same axis and the rotation is also about the same axis, then we call it as a twisting joint. And here, the input and output links are perpendicular always, and the rotation is about the input link axis, then we call it as a revolving joint. So we mostly use the rotational joints and twisting joints and the revolving joints in our industrial robots. Now let us try to classify the robots. There are multiple types of classification based on certain parameters. So now we are classifying it based on the space that a robot can move. The first one is the Cartesian, the second is cylindrical, the third is the polar, the fourth is the angular, and the fifth is the Skara. The Cartesian, so mostly the moments are along the XYZ axis. So typically the workspace would be a cuboid, a rectangular cuboid. So which can be achieved by means of LOO, which means a linear joint in vertically and the orthogonal joint perpendicular to the linear joint and another orthogonal joint to the second link. So with this LOO configuration, we can able to achieve a rectangular cuboid space, which we call it as a Cartesian robot. And also it can be called as a gantry robot. Mostly you can find these things for the pick and place applications. Even in the 3D printing, the FDM machine, you can see which also works on the similar principles. So these gantry robots use this Cartesian configuration. The next is the cylindrical configuration, in which we can use TLO. So T for the twisting over the base on its axis, and then L for the linear, so which slides over the vertical axis, and then perpendicular to this link, so that is the orthogonal joint, so with which we can get a cylindrical space. So the robot can move within this cylindrical space anywhere to reach a specific part to do a specific operation. So there are some altered configurations other than the TLO. You can get the same workspace with TLL, LTL, or LVL configuration. So here is some example. And the next is the polar or the spherical robot. So in which the type of joints are TRL, T for the twisting over the axis of the base, and then the rotation. So which is the rotation is perpendicular to the twisting axis, and there is a sliding in the other direction, that is the linear joint. With the twisting and the rotation and then the linear, we can form a polar robot. So the polar robot, the space is typically in a spherical shape, which we use it for a movement along a contour. The contour supposed to be the highest of second degree order. So you can use it for a cylindrical application. You can use it for a welding applications as shown here. The fourth one is the angular robot. Mostly we find these angular robots for the manufacturing applications, in which most of the joints are the rotational and except the twisting over its base. So we can achieve this angular joint with a TRR. So here you can able to see the work volume of an angular robot. And the final is the SCARA robot, so which is specifically designed for the assembly operations. The SCARA stands for Selective Compliance Assembly Robotic Arm, so which generally do the simple insertions, the peg and hole assembly operations, which can be done by these SCARA robots. So the SCARA robots is having TTL, where two twisting to move within the space, and L is the linear one to pick the object or to place the object. So this is the classification of robot based on the space. And the next classification we can do based on the mobility. So most of the industrial applications, we are going to use the fixed robots, which means the base is fixed. The other arms would be moving to reach the respective locations. The second classification is the moving robots. So the movement can be given by the legs or by the wheels. So here you can find out some fixed robots where the base of the robot is fixed. The other arms of the robots are moving within the dexterous space. In the moving robots, you can see here, which is taken from the Boston Dynamics, the big dog. Nowadays, it is also used for the manufacturing applications, specifically in the material handling and palletizing. So the wheeled robots are used mostly for the surveillance and inspection purpose. The third categorization of the robots is based on the control systems. So the first one is the point-to-point control system. So here you do not have a control over the path, how it has to move from the start point to the end point. The second is the continuous path control. So where you can define the path of the robot. So the robot will move along that specific path by interpolated points along the curve. It can be a straight line or it can be any second or higher order curves. And the third one is the intelligent controller. So in the intelligent controller, you are not just stating the start point and end point. You can also define the environment, which means the obstacles presented in the environment. So the controller has an artificial intelligence system which can able to derive a path, a collision-free path which avoids the obstacles and move from the given start point to the end point. And now we are moving to the characteristics of the robot. So these characteristics further will be used while buying or selecting a robot for a specific application. The first characteristic of a robot is the payload. The payload tells the ability of the robot, how heavier objects that it can lift. The next is a repeatability, which is the ability to position back to a certain point. So when you do the repeated tasks, the repeatability is the major concern. The third thing is the accuracy. So when you do the precision manufacturing, the accuracy plays a significant role. So which is the capability to position the tool at a targeted point in the work volume. The fourth one is the spatial resolution. This is the smallest movement of the tool can be controlled by the robot. So each robot is fixed with certain end effectors that we are going to cover in the forthcoming slides. So those end effector can be the grippers or the tools. So the smallest movement of the tool can be controlled by the robot, can be defined as a spatial resolution, how precise the movement is. Now let us look into the elements of the robot. The first one is the power supply. That is the obvious requirement when you install any robot. The second one is the controller. As we discussed the categorization of the robot based on the controller. So we need the controller for a specific moment of the robot. And then the end effectors. End effectors, the name itself it is showing. So we are going to attach this at the end of the robot arm. So end effector can be a gripper or a tool. And the fourth one is the actuators, which acts as a power supplier. So it can be a mechanical, or it can be a pneumatic, or it can be a hydraulic power source will be there to actuate the links. And we need the actuation for the both the robotic links and also to the end effector. So we have to ensure the compatibility between these, the power source for the actuators and the end effector. The fifth one is the arm or the manipulator, which is the skeleton of the robot, the base and then the links and joints. The sixth one is the drive mechanism. We have a specific session on these drive mechanisms. So this drive mechanism typically located at the joints to give the moments to the links. These are the main elements of the robot. Now let us get into details. So first we are going to see the grippers and then sensors. It's typically the end effectors and sensors. So an end effector is a device which is attached to the wrist of the robot arm and enables the robot to perform the tasks. See, when you compare the robot with the human, we call it as the base, and then whatever the links are there, we will just compare with our shoulders, arms, and then wrist. So the wrist is the most, the end point of our human arm, where we have the palms. Without palm, with simple shoulder and arm, we cannot able to perform any task. Similarly, the robot also cannot perform any task unless and until you attach some end effector to the end of the robot wrist. So here end effectors can be categorized into two types. The one is the grippers, another is the tools. The grippers are generally used to grasp an object and hold the object. So this is typically used for the loading and unloading and pick and place. The other type of end effectors are the tools. These tools are basically on the specific application of the robot, it will be changing. For a spot welding, painting, arc welding, inspection, we will be using different type of tools. If you look at the grippers, there are multiple grippers based on the mechanism and the power source and the technology that we use. The mechanical grippers, which basically works on the pivot based actuation or a linkage based actuation or the gear based actuation or the cam based actuations. So we can give the actuation to the gripper in many of the ways based on the mechanical energy. So you can see all the four categories. And the next one is the vacuum based grasping. So vacuum based end effectors are mostly used in the industrial applications because they are so precise. So here the vacuum cups are the suction cups, which are made up of some elastic materials such as rubber or plastic. So it works based on the difference between the atmospheric pressure and the negative pressure. So based on the weight of the object, the surface area of the suction cup can be enhanced. So the pressure multiplied by the area would be the total weight of the object, what we are going to lift it. So these vacuum cups or the suction grippers, which we cannot use it for the parts with holes because we cannot able to create it. And also at the irregular surfaces, also we cannot use the vacuum cups. So that is the biggest limitation with these vacuum grippers. The next one is the magnetic grippers. So here we have two types of magnetic grippers. One is a permanent magnet gripper. Another one is based on the electromagnetic grippers. So in the permanent magnet grippers or both these magnet grippers are used to hold the metallic parts, typically the ferrous parts. So the, the magnet grippers are so precise at their function. So here you can watch the video. So here you can see this is an electrical gripper, electromagnetic gripper. So here the air is pumped. You can see this, the air is entering either at the top or the bottom so that it can load and hold the object. You can see this suction grippers, you cannot use it when there are pores or the holes. You can see even this mechanical grippers doesn't work well, where you can use this magnetic grippers. So this is an electromagnetic gripper. You can see for a pick and place operation. So this is typically for a precise pick and place application. We can use this magnetic gripper. Now we will see the other type, that is the adhesive grippers. So in the adhesive grippers, so the adhesion to the gripper is given by means of some tacky thing. So whenever it uses the tackiness, these adhesive grippers cannot be used for multiple instances. So in this adhesive based grippers, so it will stick to the object and then lift it, and further it will release it. The adhesive grippers are not very much used in the industrial applications. The other type of grippers that you can see here, such as hook kind of devices, and you can see the scoop kind of devices. These scoop kind of devices are generally used to take some powdered material or in granular form. You can just use it, this scoop kind of devices. Even for the liquid also, the molten metals as such, we can use this scoop kind of devices. And some flexible grippers and these compliant grippers. The compliant links itself, it's a separate subject. So we can use the compliant links. We will see this in the human robot collaboration, how these compliant links are much better and useful for the industrial robots. So these are certain other categories of the grippers. And now let us look at the tools. Basically, we use the tools based on the application where we are going to use the robot. Maybe for the drilling purpose or the inspection purpose, or for the painting purpose, or the welding, arc welding, or the spot welding. The tools will vary accordingly, or for the assembly purpose. Now, whenever you have an end effector, you have to fix this end effector to the robot exactly at the wrist. So there you have a face plate. So to the face plate, you are going to fix the end effector. So whenever you whenever you use a robot, we clearly notify the payload of the robot. We always ensure that the weight of the end effector plus the weight of the component that it's going to handle together should be considered for a robot payload. If at all any damage occurs to the robot, that costs very high, and hence we are going to place some kind of shear pins or sensors, so which can able to find out the weight of the gripper and the part together, and then it can disjoin from the robot, so that there will not be any damage to the robot. Whenever you are fixing an end effector to a robot, we also must ensure the kind of actuation or the power source for the end effector to perform the task efficiently, because the robot will give its own movement, and in coordination with that movement, the power source should also actuate the end effector to complete the task efficiently. And in addition to the grippers and tools, we also have the sensors. So a sensor is a device which is used to measure a property such as pressure, position, temperature, acceleration, and also to respond with the environment, the manufacturing environment, the surrounding environment, and to give the feedback. Here we have 4 types of sensors given here, 5 types. The proximity and range sensors, vision sensors, touch and force sensors, light and sound sensors. So other than this, we do have the electrical or thermal sensors, so that we are not going to discuss. A proximity sensor is a sensor which is able to detect the presence of a nearby object without any physical contact. Here you can see the working function of an inductive sensor. Here we have 4 different types of sensors, proximity sensors, which works on based on the inductance, capacitance, and magnetic and ultrasonic. Ultrasonic sensors also called as the range sensors, so which is used to find out the depth to the nearest surface, so to how long the object is positioned, that we can find out through these ultrasonic sensors. The next is the vision sensors. So vision sensor is not just a simple camera, so there will be a calibrated system along with the camera, and there will be a lighting system so that it can able to work in a dark environment also. So these vision sensor are typically used for identifying the object mostly and detecting the objects. And the next is the tactile sensors. Under the tactile sensors, we have touch sensor and force sensors. So touch sensors mostly we have seen in our day-to-day life, in our mobiles. When you give your thumb impression, then only it can get locked or unlocked, and even in biometric attendance as such. So this recognizes our touch and then give the response. So piezoelectric materials are used to sense the touch and then response in terms of electrical signals. And then the force sensors, you can see this video of force sensor, which is able to detect and give the feedback in all 3 forces and 3 rotations, the moments, Fx, Fy, Fz, and Mx, My, Mz. So you can see this force sensor can be used for contact, alignment, probing, and following and press. And mostly we are going to use the combination of these 3 things for the assembling and manufacturing. Here, this demo shows you how this force sensor can be used for each independent task, and how it can also be used for a collaborative task for a specific manufacturing application. So this is an example for the contacting. If the contact is based on the contact, it sends the force, and the misalignment also can be detected, and accordingly it gives the forces. You can see the force, how much force is required. This arrow blue and red, it shows. So along X and Y, how much force supposed to be given so that it will slide. Now only in the Z direction, the moment. You can see this Z direction, the force for the alignment. See here a combination of contact, flow, and then the press. For the screwing and also we can use it for the riveting and unscrewing as well. For the alignment purpose, we need contact and follow and then align. You can see the change of forces in X, Y, Z directions and the moments when it is aligning. So the next is the light sensor. So in the light sensor, we have a IR light emitter and a detector. Detector typically a photoresistors which can able to detect the light which reflects from the object. In presence of no object, the light only emits from the IR light emitter and it just goes. If there is an obstacle or an object, then the light can be reflected, which would be sensed by a photoresistor, which is used to identify the object. And similar to the concept of light sensor, the sound sensor also works. Here you can take the best example of our ear, how it works. So it has a diaphragm with magnets that are twisted with the metal wire. When the sound signals hit the diaphragm, it vibrates and current can be stimulated from the coil. So you can see so now I am not covering the concept of thermal and electrical sensors. And we have a specific session on intelligent sensors and the sensor fusion for the industrial robot, maybe on tomorrow. If you have any further queries on sensors, you can explore more in that session. Now, I'm taking you through the robot selection. When we are going to select the robot, the parameters to be considered, the first is the degrees of freedom. So this will tell you the reachability of a specific location, and the power supply which we are going to give to the robot and also to the end effector. If we are going to take the robot for material handling, for the welding or for the spray painting, so whatever end effector that we are going to assemble to the robot, for that also we have to check for the power sources. Then the control system, maybe the continuous path control or any other intelligent controllers in which you can write your own program. And then the maximum payload of the robot and the reachability of the robot within the working environment and the application where we are going to use the robot. Then comes to the accidents and safety. So in general, on normal working conditions, generally we do not find out any accidents with the robots. Most of the robot accidents occur only during the programming stage, programming and testing stage, or the maintenance stage, while repairing or testing or the adjustment stage. So typically the links are so rigid and they are weighing very high payload. So there will be a high energy movements in the workplace. So which can able to create a significant impact or the hazard if the human stands inside the work volume of the robot. That's the very basic reason the robot is completely and clearly isolated or separated from the human working environment with a fencing. So now in the industry 3.0, the robots are working within the fencing, and industry 4.0, we are moving towards the fenceless robot with fenceless cooperative robots which can work in collaboration with the humans. So typically the type of accidents can be a impact or a collision. So this is a testing of the effect of the impact or the collision if the robot hits a human within its environment. So the other one is the crushing and trapping accidents. So if at all any part of the human body, like the limb or any other body part, if it is trapped or crushed inside the robotic peripheral equipment or arms, so one must have to take care. So for this purpose, you will be having the switches, or you can follow the robot off man on or man off robot on conditions, so that you can avoid these kind of accidents. And the fourth one is mechanical parts accidents. So these generally happen due to the breakdown or release or failure of the parts. If we do not do the appropriate maintenance frequently, these mechanical part accidents typically occurs. We have a special session even for this accidents and safety by an expert from the industrial safety background. So here you can visualize certain failure of the machine during the running condition, because a heavy payload is there. So sudden failure, you can find out at this particular joint, it could not able to hold the entire weight. So the source of the hazards can be the human errors or improper controlling, unauthorized access to the robot, and the mechanical failure of the equipment, and the surrounding environmental sources, and improper installation or improper calibration of the robots. Now we reach to the application of the industrial robot. The robot can be used in multiple industrial applications, which includes the inspection, the assembly, and the cleaning. Typically, you find cleaning in case of energy sector and electronics sector. You need a clean room when you work with the nanotechnology. You have a clean room robots. And the gluing means when you use the adhesives to create the laminates. When you do a composites laminates manufacturing for an aircraft industry, you are going to use robots for the gluing. So it will apply a uniform thickness glue to the laminas. And then water jet cutting, where the precision is very high important, and as well as it is so hazardous a human to work within the environment. And the painting, sometimes the paints are so toxic in nature, the human supposed not to inhale the paints. So the robot painting is one of the very common thing which you can see in aircraft industries. And whatever you see, if you want to paint such a big equipment, the machine, so it cannot be done by the humans. So mostly the robots are used for the painting for the aircrafts and automotive transportation vehicles, where you can get a uniform layer thickness with high precision. And the laser cutting. So laser cutting is used in multiple manufacturing industries for the composites as well as in sheet metals, where we can use the robots. So in the example of magnetic grippers, we have seen that the magnetic grippers, it absorbs or it grasps a sheet metal where the sheet was cut by means of the laser cutting things. And then the arc welding and the spot welding. The robots are the highest used in the manufacturing industry for this purpose, arc and spot welding, where a consistent movement of the tool is given, and we get the same accuracy throughout the weld specimen. So that is the advantage of a robot used for the spot and arc welding. And then the machine loading and unloading. And typically this is a repeated task where a human can tend to a fatigue due to the repetitive task. So robots are very much used for this machine loading and unloading applications. And finally the material, and when you want to transfer the material from one location to the other specific location, the robots with some artificial intelligence is very much helpful to handle the material within the warehouses. And then the palletizing. So the robots are mostly the highest used in the welding, then machine loading, unloading, and material handling, and then the assembly. These three are the highest stake. You can consider it almost some 70% of robots, industrial robots, are used for only these three applications. Now we came to the final one, the installation checklist. If we want to buy a robot and install it, the checklist to be considered is the first thing is the utilities in the cell where you are going to place this robot. So the utilities typically comes as the space, how much you have to keep the robot, and what will be the power source, whether it is electrical, pneumatic, or hydraulic, and what kind of transmission that you are using. The second thing is the placement of the robot. What happens? An industrial robot generally work with the coordination of many other equipments and conveyors, production machines, fixtures, and tools. So what happens? Where exactly you supposed to place the robot so that the material transfer from the robot to that other parts of the machinery should be the material transfer rate supposed to be optimized. So based on that, we are going to decide the placement of the robot. And then next thing is the other supporting units like material handling, and then the base part mounting for the assembly, the base part mount assembly and the welding, the base part mounting units, and the conveyors to move the parts, and inside the cell and outside the cell. Once the robot complete the task, human cannot enter inside the cell, so the parts will be sent through the conveyor to outside the cell. And then the calibration we supposed to do. Once the robot is placed, we have to see whether the controllers are working efficiently, and then the appropriate communication between the controller and robots, and then the interlocks and the sensors. Interlocks are the switches which we use it for the intermediate start and stop, and then the other accessories like the sensors, the vision or eye or range sensors, whether are those working in line with the applications. Finally, the safety systems and then the grippers. So with this, we will verify and calibrate the entire robotic work cell. Instead of a robo, I can say it's a complete calibration of the robotic work cell. Once we do this, we can go for a trial production run. If the trial production run is fine, then we can go for a real-time production. So this would be the installation checklist for an industrial robot. When it comes to the future industrial robots, you can just look at this, a collaborative robot by KUKA Robotics. So where the human and robot, they have to work together to do a task. Human may not able to do the task with high precision, so we need the robots. But when the robot is moving, it should suppose not to harm the human. So the human and robot together, they are working in collaboration. So these are certain applications of human robot collaborations in the aircraft industry. So you have seen the collaboration between human and robot to do a specific task. Still, we have to achieve a lot in the collaboration. So that we are going to see in tomorrow's session. The different types of human robot collaboration, why it is needed, and what are the existing technologies and challenges and future scope in the human robot collaboration. We are going to see one more short video. This is from ABB Cobots. You can see the machine flow line. The reason here, when you use the cobots, the workspace is so much of reconfigurable. So, and it is so flexible. And day to day, we are coming up with new methodologies, new manufacturing processes, new products. You can see if a person enters inside the grid, you can see when a person enter inside this, the robot sphere, so immediately there is a red kind of sensor and it stopped working. And here you can see the green, so which indicates that this robot is in working conditions. So as I told you, previously the robots are given with the fences. Now the fences are remote, and there would be some sensors to identify the presence of the human and to interrupt the process of the robot so that it will not harm to the human. So the finally we are going to see one more video on self-balanced robot by Boston Dynamics. So most of you might have seen this Boston Dynamics robot before, which can capable of going in multiple terrains. And here it is used for material handling with a highest load carrying capacity. So it can able to hold up to 20 kgs, I think. So there are multiple pallets are placed here. So per hour it can able to move 200 pallets per hour from a specific location to the conveyor belt. The back side, the tail kind of thing, which you can see here, the hanging one, so which give the balance to this entire robot. So the robot is completely moving on the wheel so that there will not be any friction while the moving, and it can use a minimum amount of energy for moving from one place to the another place. You can also see these suction cups or the vacuum grippers. Since the surface is very flat, these vacuum based grippers can be used or managed to pick and place the pallets. So we can expect a lot and a lot in the industrial robot segments. So with a multi diversional scope for expansion in terms of the sensors, in terms of controllers, in terms of optimizing the things, in terms of the collaborations. So with this, I'm concluding my session. So there is a lot of future scope for the industrial robots. And the upcoming sessions are dedicated mostly on the advanced topics. So thanks for listening. If you have any queries, you can ask the queries, please.
We are very thankful for your valuable expertise, Dr. Raju sir. This session enhanced our knowledge and enlightened the understanding about the role of industrial robots and meeting Industry 4.0 requirements. Now participants can ask their queries regarding this session.
Yes, please. I request the participants, if you have any queries, you can ask me now, or you can also contact me at my mail ID, which is given on the screen. So I can able to see one question about the employability. This is a very strange question asked by the technocrats. Uh, See, we are developing we are developing the technologies. So, if you see the olden days, the Industrial Revolution 1 or Industrial Revolution 2, Industrial Revolution 2, where the mechanization has taken place, we replaced most of the human with the machines. Now, what happened? The production of the machines and their spare parts, now it got boom, right? So automobile is there, automobile spare parts industry, now it has become the biggest one. Now we are going to use the robot for the manufacturing applications, and we are not replacing the humans with the robots, we are replacing the machines with the robots. You have to understand clearly that. And now we need lot of workforce to increase the capabilities of the robot in multi dimensional towards the intelligent controllers and towards human robot collaboration. If you see in the industry 4.0, we have once again moved from the fixed automation to the flexible automation. Once again, in the flexible automation, we are using the human and robot in collaboration. So we must understand one thing: when we are developing a technology, the associated technologies also will develop. And only thing we need to improve our skill, rather blaming on the technology, that assuming the technology will wash out the jobs. In fact, the technology will not wash out the jobs. The people or the workforce have to develop their skills to suit for that particular requirement. Yeah, any more questions? Participants cannot mute their. I think you can unmute on yourself and you can ask the queries, please. Can you please unmute yourself and you can ask the queries? So is there any robot manufacturing company in India or Asia? Yes, there are many manufacturing companies within Asia. So, and mostly we have here the assembly units than I can say manufacturing units within India.
Hello, am I audible, sir?
Yes, 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 please.
Yeah. Myself, Dr. V.L. Krishnan from Vijayawada, VR Siddharth Engineering College.
Yes, please.
I want some little insights about a special type of sensors, some if they are being used for cobots.
Yes,
like
sir. Got it. So there is a special session designed for that intelligent sensor and their fusion for the industrial robots. You kindly attend for that, sir, and your queries will be addressed through that.
Okay, sir. Thank you.
So this is Gurpreet. Actually, one question. We have seen these robotic arms in the assembly lines. So is there any possibility of using the robots for with coupled with artificial intelligence to drive a car?
Yes, sir. Yes. Yes, you can, of course, use it, sir. I'm going to share you some links where you can use these robots with artificial intelligence for multiple functions.
Yes, in that case, we'll be having a complete robot in a form of a body or like a human body, or we'll be having like actuators with sensors.
Sir, it's up to you how you design it, sir.
Right.
Because the degrees of freedom and flexibility, what you need is matters. If you need more flexibility and more degrees of freedom, then you can inspire from the human, because we have a lot of flexibility and degrees of freedom. If you don't need any flexibility and degrees of freedom, you can just simply make out with a simple thing.
Okay, sir.
Yeah, I have seen one question from Dr. Dinesh W. Rathod. In which area of robotics the specific R&D can be focused? As much of industrial areas already having the readily available robots or robotics. Okay. See, sir, now probably I think the next session, the upcoming session, tomorrow session may address your query well, but I'm giving you a hint. So here, the precision manufacturing is the one critical area. Now robotics are booming up. And then the second thing is the flexible manufacturing with mass production with mass customization, where the robots need to be integrated with multiple technologies like augmented reality and then these IoT systems as such. So those two are the critical areas currently the R&D is focused.